Good afternoon, class. In today's video, what I'm going to do is go over the derivation of the final velocities for a head-on elastic collision. I'm going to do this in the general form, and as a reminder, this is going to be an intermediate level video. So again, if you're working on this from the most basic, I'm only testing on the most basic materials. This is for those who want to go a little bit more in depth into how all of these equations get set up and how they function and where they could possibly go, as you go further into physics and learn more about how everything comes together. This is where the math portion of it gets kicked up quite a few notches. So in this one, don't worry, you don't need anything more like calculus or anything like that. This is more of algebra, but still you're going to need some algebra in order to follow along with this, because as you can see, I wrote a lot. This is a lot of material to write down on the board. I'm kind of almost out of frame because I can barely fit all of this stuff into this video while I'm trying to talk about it. So I'm going to be doing what I can. I've got my magic ruler here to really point my way to all of the different answers, and I even tried to do what I could to make sure that I broke it up into different parts, because there's just so much to write and so much to go over, but we'll get there. And so what I want to start off with is the basic principles. How do we get a head-on elastic collision, and why does this even how do we even work this magic? Okay, and so we start off with some general principles, and that's really the most important lesson that you need to take away from, is that if you want to ever get an equation, because this is the final result right here, if you ever want to get to here, it's not just getting through all of this math that's important. You actually have to know which equations to start with at the beginning, and that's why I start off with what I wrote everything here in black, to give you the basic first principles to get you started into this journey to get to these last equations right here. But I believe it's worth it as long as you're willing to put in the work and really willing to start from first principles. You will get very far in terms of getting all of these really amazing equations and be able to use formulas that you didn't think you would be able to, simply because they're not necessarily provided in the textbook. So let's do this. We're going to start with the general principles first, then we're going to solve for V2 final, and then we're going to solve for V1 final over here. And I'm going to start on this side because when I get to V1 final, I'm going to start moving into the frame a little bit, pointing a little bit more over here like this, so I might be covering up what is written over here. So if at any point you need to pause this video so you can see this derivation in its entirety, that's why I'm kind of standing over here, so that you can, do that. Pause the video, take a look at what I've gone over, and then, restart wherever you needed that pause. Okay, so let's start with the basic principles first. To get an elastic collision, there are two things that must be true. One, the momentum must be conserved, and two, the kinetic energy of the collision must also be conserved. So if those two things are not true, either one, you didn't have a collision because momentum has to be conserved, and two, if kinetic energy wasn't conserved, then you probably have an inelastic collision instead of an elastic collision. So those two things are very important. So what I wanted to do was write out the conservation laws over here at the top. So that's why P1 initial plus P2 initial is equal to P1 final plus P2 final. For those of you who are a little bit further along in your mathematical journey, you might recognize this symbol over here. So I call that this is the Greek letter sigma, and so you could also rewrite this entire thing, because this may seem like a lot to you, but you can write it as sigma p is equal to 0, or the sum total of all the momenta in the entire system will come out to 0, which is to say momentum is conserved. Same thing with kinetic energy. The initial kinetic energy of the first object plus the initial kinetic energy of the second object is equal to the final kinetic energy of the first object plus the final kinetic energy of the second object. Or if you want to really summarize that, the summation of all of the kinetic energies is 0 because kinetic energy is conserved. So, and just as a couple of notes here, that's why I'm going to point this out. I wrote this down. So this symbol over here means the summation of in math terms, or the sum of all of, or the total, whatever comes next, is what this is supposed to represent. It is also the Greek letter capital sigma. So if you're looking for any of those, like what all of that means, that's your explanation. Hopefully it's all tied up neatly in this one video. All right, so now we're ready to get into the weeds of all the details of how to solve this. So let's do this. So first, we're going to solve for, so the problem is initially we've got these starter equations, and we're going to solve for V1 final and V2 final. So the scenario is this. You've got a head-on elastic collision. So you can think of it as two bumper cars smashing into each other head-on, and we're going to assume that V1 initial, V2 initial are given values. So the question is, what is V1 final and V2 final? So if you've got two bumper cars and they smash into each other, what are their final velocities going to be at the end? So now some of you might be starting to get some kind of instinct about this from your math classes. You might start to think, wait a minute, I can't solve this momentum equation for two variables because I only have one equation. And you would be correct. If you want to solve for two separate variables, you need two equations to do that. And that's why we have this conservation. These conditions actually make it perfect to actually solve for both V1 final and V2 final independent of each other. And that's what we've been doing. That's why I did V2 final in blue and V1 final in red. Okay, here we go. So we know that the sum of all of the momenta is 0, and this symbol means which leads to. So sum of all momentum is 0, which leads to the what I wrote earlier, right up here. I just, instead of writing P, I wrote MV. So I'm going to move everything to the, I'm going to move all the V1s that I see on this side of the equation to this side of the equation. I'm going to move to the left side, which means naturally I'm going to move all the V2s to the right side. But I did that, I moved all the V2s to the right side. I wrote that in red so that you can see where my transition comes in when I solve for the second of the two variables that I'm solving for. Okay, here we go. So I'm going to solve for V1 final, and I'm going to substitute it into the conservation of kinetic energy. And I did skip, now I will warn you on this one. This is why you may want to pause at some point and maybe fill in some of these steps in practice, because I did skip a lot of steps. In fact, this substitution into the kinetic energy formula, I probably should have written somewhere over here to give you more of a guidance on where that was. But as you can see, I've basically filled up the entire area of this video with all of my work, and this was condensing everything, skipping steps and all of that. So there's a lot that I actually can't show you on here because it takes too much space. So if you want, let me know though if you do want to see like a full derivation with all of the steps included and in excruciating detail. I can do that, but I will have to do it. I'd have to break it up into at least 2 videos to pull that off. However, if you're just looking for, if you're willing to put in the work and at least do those those in-between steps, those algebra steps, then you're fine. So let us continue. So I start with my equation up here. I'm going to solve for V1 final on, I'm just going to isolate my variable. And so I've skipped all the steps on how to isolate the variable because, again, 1, I don't have time, and 2, I don't have space. So here we go. The result is V1 final is equal to V1 initial minus M2 over M1 times the difference of V2 final minus V2 initial. There will be a lot of get ready, buckle up for this because there's going to be a lot of variables that I'm going to be talking about. So then I put this one in, the summation of the kinetic energies. I put that equation in, which was again what I wrote over here. Just instead of Ke for kinetic energy, it's 1/2 mv squared. So when I put all of that in, what I noticed, the first thing I noticed is, oh, all these 1/2s can cancel each other out because I just divide the entire equation by 1/2 and I'm fine. Or for those of you who don't like dividing by fractions, I multiplied every term in the equation by 2, the opposite of 1/2. So what I get, and so then what I also noticed was, well, if I'm going to do that, I might as well, I'm going to try and get rid of as many variables as I can. What I'm trying to do here is actually isolate, I'm going to actually try to isolate either V1 final or V2 final. So what I did was I said, well, if I'm going to divide by 1/2, I might as well also divide by 1/2 M1. So so from here, I got rid of the M. I divided M1 on both sides of the equation, so I got V1 initial squared plus M2 over M1 V2 initial squared equals V1 final squared plus M2 over M1 V2 final squared. I realize that I am speaking very fast, and I have also realized that you could probably read this as well. I just wanted to make sure that you heard me say it, plus the fact that you can read it yourself. So just know that if it sounds like I'm just kind of reading what I'm writing out here, that's just because I want you to be exposed to the information in 2 separate ways. Okay, so we go to the next step. And now that I've done that, what I'm going to do is I'm going to solve for V1 final. But in order to get there, I have to I have to move this term over to this side of the equation and move everything here, move these 2 terms to this side of the equation. So I did that. I collected my terms, but not only that, I noticed that I've got V2 final over here, and I've got V2 initial over here. Plus, they have a common factor of M2 over M1. So I collected those terms to make sure that it kind of looks a little bit simpler. So now that I've done that, what I'm going to do is I'm going to go back to my original equation right up here, V1 final equals this, and now notice what I've got. I've got V1 final squared is equal to this result, or this thing. I know that V1 final is equal to this thing. So what I'm going to do is I'm going to substitute V1 final into this equation of V1 final squared, and I'm going to then do a bunch of algebra to solve for V2 final all the way at the end. So here we go. I plugged in V1 final into V1 final squared. And notice this area right here, that what I wrote here is exactly what I wrote over here. When I plugged it in, I'm not going to read this whole line to you, so just know that that's not going to happen. But once I got all of this done, I noticed that I have V1 initial squared on both sides of the equation. They're both being added, so I just subtracted them from both sides of the equation from each other, so that canceled out. Then I took a step, because then the next step I took was I saw that there's this parentheses V2 final minus V2 initial here. This one is being squared. And then I've got this difference of squares here. And what I remember from either algebra or algebra 2, the difference of squares, I can actually write that out as V2 final minus V1 initial parentheses times parentheses V2 final plus V2 initial. And when I saw that, I realized, wait a minute. Something is here. There's a common factor of V2 final minus V2 initial. Now, you have to understand something. When I'm going through all of this, I really don't want to make this, I don't want to give myself a whole bunch of extra work. So what I do is I look for common factors that I could possibly divide out. With keeping the caveat, of course, that if at any point some of these turn out to be 0, I've got a problem. But in most cases, that will not be the case. So me dividing out all these extraneous roots or these extraneous factors is not a problem. So I take my next step and I write out that V2 final minus V2 initial, and then I can cross that out here, cancel that out here, because I divided both sides of the equation, all the terms, by V2 final minus V2 initial. This is squared, so that's why there's a little slash on that square, because I've canceled out that power. So now what I'm left with, oh, and then also I noticed that every term had M2 over M1. This one was squared, so I just divided everything by M2 over M1. So what I've got left is 2 times V1 initial minus M2 over M1 times V2 final minus V2 initial equals V2 final plus V2 initial. I'm almost done. We're almost there. Because what I'm going to do now is I'm going to collect all of my V2 final terms, move them over to the left side of the equation as much as I can. And in order to do that, I'm going to collect my terms, put everything together, and then, I have to admit, I don't really like this over M1, mostly because I don't like fractions. I mean, I don't like decimals a whole lot more than fractions, and so I will settle for fractions any day of the week. But if I can avoid fractions as well and just get just symbols or just whole numbers, I will take that. So what I did was I multiplied everything by M1. So I got this line, which for the sake of time, I'm not going to read that to you. I feel like you can read that yourself. And then I divided both sides of the equation by M1 plus M2 because that was the common factor to help me isolate V2 final. So I finally get this answer, this wonderful answer right over here. I'm not going to read that to you because, again, you can see that. But this is the result. If you have a head-on collision with two things moving, your final velocity of the second object will be given by this relationship. Now, a lot of times, especially on physics websites, it'll give you the relationship assuming that the other object was started at rest, and you can do that. And if you plug in those values for let's say v1 initial was 0, then you've got the relationship that the physics websites would actually tell you. So this works. It's just that I wanted to show you the general result because, otherwise I would have just told you, look it up online. It would have been fine. Okay, so here we go. Now I'm going to hope everyone had a chance to look at this and copy that down or absorb that information because I'm going to start going over to this red section, which means I'm probably going to get in the way of this part. So here we go. This time, we're going to do the exact opposite of what we did over here. Instead of solving for V1 final at first, I'm going to solve for V2 final. Because once I get to this part, I know, at first I thought, oh, I'm going to solve for V1 final, and then I'll get V1 final at the end. But it turns out that I actually solve for V2 final. So I know that if I do the opposite, I start solving for V2 final here, I'm going to end up with V1 final at the end. So same thing, so I'm basically going to do the exact same amount of work. I'm not going to go into this one nearly as much because really all the work that I did here, I did over here, except over here I skipped a whole bunch more steps because I already showed you those steps here, so I skipped some. I combined steps as I could over here. And again, I'll let you look at this and check that out, just especially for the sake of time. But I started with V2 final, solving for it. It looks pretty much the same as this one. And then I go through all of the same types of steps again, and what you notice is I get pretty much the same relationship. However, there is one difference, and I do want to point that out. If you notice over here, this V1 initial term has M1 minus M2 over M1 plus M2. This one has M2 minus M1 over M1 plus M2. So, I want to point that out because it's not like you can look at this and say, aha, they are interchangeable. They're not. There's actually a difference which one you pick as the first object and which one you pick as the second object, and it depends on which one is moving, which one is, and which direction is actually positive, because whichever object you pick, honestly, it doesn't matter if you pick something as V1 or V2. It really doesn't matter which one of these you pick, but it does matter in terms of, because the general convention is that the first object, or the thing you give V1 to, is going to be going in the positive direction, which, at least if we're going by the way the board is facing, is to the right. And then V2 would be traveling in the negative direction, or to the left. So, I just want to, give that as an idea. Like, keep that in mind. So people would assume that this object is traveling in the positive direction, whereas this one would be traveling in the negative direction. Hence why you might think, oh, that's why there's a difference between the two in terms of which way the negative sign reads in this formula. So just keep that in mind. They're not interchangeable. There is a difference, but you do, again, as a physics student, you do get to pick which one of these is V1 and which one of these is V2. Just know that sometimes there can be that little bit of a difference depending on which way you declare as positive and negative, because that will actually ultimately matter, because as you can see, there's a lot of positive and negative signs in here. So that will actually determine a lot of times, how everything kind of plays out. So beyond just using the right, to summarize basically, beyond just all of these conservation laws, making sure that all of that is in a row, all of that is taken care of. The other thing that needs to be taken care of is which way you declare to be positive and negative, because otherwise you might be introducing an extra negative when there shouldn't be a negative introduced. So, and that can really throw things off. So please keep that in mind. But this is how to derive the results for a head-on elastic collision. The more general result where it doesn't matter if one is at rest or the other is not at rest. So good luck in your studies, and may the force be with you.